Water source heat pump, WSHP systems are one of the most efficient, flexible, and scalable HVAC solutions for commercial and multi-unit residential buildings. Unlike traditional central systems, WSHPs move heat rather than generate it, functioning like a BTU battery, redistributing energy throughout the building for heating and cooling. They offer simultaneous heating and cooling across different zones, high energy efficiency through shared hydronic loops, ease of design and maintenance compared to chiller boiler plants. A commercial WSHP system connects multiple individual heat pumps to a common hydronic loop. Each WSHP serves its own zone, for example, an office, classroom, or apartment, extracting or rejecting heat to the loop as needed. The loop itself is kept within a broad temperature range, typically between 60 to 90 degrees Fahrenheit. If the water gets too warm, a cooling tower removes excess heat. If it gets too cold, a boiler adds heat back. This keeps the system in balance, ensuring each zone can heat or cool independently at any time. The beauty of WSHP systems is their simultaneous heating and cooling capability. While one part of the building may require cooling, another may need heating, and both can happen at the same time using the same loop. This internal heat recovery makes the system extremely energy efficient. Key advantages of WSHP systems: A. Installation and operational flexibility. Each WSHP unit can be installed above ceilings, in closets, or in mechanical rooms. This modular approach minimizes ductwork and simplifies maintenance. Each zone operates independently, though all can still be monitored via a central building automation system, BAS. B. Space efficiency. WSHPs use small diameter piping to carry large amounts of thermal energy. For perspective, a 2-inch water pipe carries the same cooling capacity as a 24-inch air duct, saving significant ceiling space. The loop can also serve domestic water heat pumps, DOS units, and even water-cooled VRF systems. C. Low lifecycle costs. Installation costs are comparable to packaged rooftop units, but maintenance and energy costs are lower. If one WSHP fails, only that zone is affected, unlike a chiller or rooftop system that could disrupt the whole building. D. High energy efficiency. ASHRAE holds WSHPs to stricter standards, 13.0 ER for cooling and 3.7 COP for heating, thanks to water's superior heat transfer. A 2,000-gallon loop between 50 and 90 degrees F can store over 650,000 BTUs, acting as an energy buffer. E. Environmentally friendly. Each WSHP has its own sealed refrigerant circuit with only about 43 ounces of refrigerant, helping comply with ASHRAE 15 and 34 standards. This makes them safe, low emission, and compliant with modern sustainability goals. Typical WSHP applications. Water source heat pump systems are flexible and fit a variety of building types. First, they're ideal for multi-story or multi-tenant buildings, where each zone needs individual control and metering for comfort and energy tracking. Second, they work well in retrofit or renovation projects because of their compact piping and decentralized design, which minimizes ductwork and mechanical space. Third, WSHPs are great for noise-sensitive environments like schools and offices, offering quiet operation and comfort. Finally, they're perfect for buildings with refrigerant limitations, since each unit contains only a few ounces of refrigerant. In short, WSHPs deliver efficient, quiet, and flexible comfort control for a wide range of commercial and residential applications. The refrigeration cycle. Explained WSHPs operate just like air source heat pumps, but instead of exchanging heat with outdoor air, they use the water loop. In cooling mode, heat is absorbed from indoor air and rejected into the water loop. In heating mode, the process is reversed using a reversing valve. This familiar refrigerant cycle is simple, reliable, and requires minimal maintenance. Let's go over the main piping design options used in WSHP systems. First, the one-pipe WSHP system. In this setup, each heat pump has its own circulator pump, which moves water through the common loop. It requires fewer valves and has a shorter installation time, making it cost-effective and simple to build. This design works best for smaller buildings, such as schools or low-rise offices. However, because the water flows in a single direction, each unit experiences slightly different entering water temperatures depending on its position in the loop. Second, the two-pipe WSHP system. Here, the system uses separate supply and return lines, so all heat pumps receive water at the same temperature. This design typically includes automatic shutoff valves to improve efficiency and protect compressors when units are off. It's ideal for larger or multi-story buildings where consistent performance and temperature control are critical. Finally, there's direct versus reverse return piping. A direct return route sends water back along the shortest path, which can lead to uneven flow. A reverse return layout balances this by ensuring each WSHP has equal piping length, resulting in better flow balance and overall system stability. In short, one-pipe systems are simple and economical, while two-pipe systems with reverse return offer superior balance and efficiency for larger installations. Finally, there's direct versus reverse return piping. A direct return route sends water back along the shortest path, which can lead to uneven flow. A reverse return layout balances this by ensuring each WSHP has equal piping length, resulting in better flow balance and overall system stability. In short, one-pipe systems are simple and economical, while two-pipe systems with reverse return offer superior balance and efficiency for larger installations. Geothermal WSHP systems, the ultimate upgrade. When paired with geothermal loops, WSHP systems reach their highest efficiency. Here, the building's hydronic loop exchanges heat directly with the earth or nearby water bodies, like ponds. The earth remains at a stable 60 degrees Fahrenheit year-round, much easier for the heat pump to work with compared to outdoor air that can vary from 0 degree F to 100 degree F. Types of geothermal loop fields. Pond loop, least expensive if a nearby water body exists. Horizontal loop, installed in shallow trenches, 5 to 6 feet deep. Vertical loop, deep wells, best for urban areas with limited land. Hybrid loop, combination of geothermal wells and cooling tower for cooling dominant climates. These systems often eliminate or reduce the need for boilers and cooling towers altogether and last for decades. The underground loop typically lasts a lifetime. A successful WSHP design depends on balancing airside and waterside components to deliver comfort, energy efficiency, and long-term reliability. Unlike centralized chilled water or DX systems, WSHPs operate as independent zone units connected by a common water loop that acts like a thermal battery. Each zone adds or removes heat as needed, while the central plant, consisting of cooling tower, boiler, and pumps, maintains loop temperature within the desired range. Calculating outside air requirements, purpose of outdoor air supplies fresh air to dilute indoor contaminants, CO2, allergens, VOCs. Improves occupant productivity and reduces absenteeism. Required by ANSI ASHRAE Standard 62.1. Ventilation for acceptable indoor air quality. ASHRAE methods. 3 accepted methods to determine minimum outdoor airflow. Ventilation rate procedure, VRP, prescriptive and most common. Indoor air quality procedure, IAQP, performance-based. Natural ventilation procedure, NVP, for naturally ventilated buildings. Most WSHP applications use VRP or IAQP, especially in humid climates. Let's calculate the required outdoor air for an office and a break room using ASHRAE Standard 62.1. The office area is 43,000 square feet with 225 people. The break room area is 2,000 square feet. From Table 6.1, the office has RP equal to 5 CFM per person and RA equal to 0.06 CFM per square foot. The break room has RA equal to 0.12 CFM per square foot. We'll use the formula VBZ equals RP times PZ plus RA times AZ. For the office, 5 times 225 equals 1125. 0.06 times 43,000 equals 2,580. Add them together. 3,705 CFM. Now the break room. 0.12 times 2,000 equals 240 CFM. Combine both spaces. 3,705 plus 240 equals 3,945 CFM. That's our total breathing zone outdoor air requirement, 3,945 CFM. When it comes to bringing outdoor air into a WSHP system, there are two common strategies. First, the direct ducted outdoor air method. In this approach, outside air is ducted straight into the occupied space. While this method is simple, it often causes discomfort for people sitting near the diffusers. The unconditioned air can create drafts or uneven temperatures, making it less desirable in most designs. So generally, this option is not preferred. The second method is to duct the outdoor air to the WSHP return plenum. Here, the outdoor air mixes with the return air before passing through the WSHP coil. This allows the incoming air to be properly filtered, cooled, or heated, ensuring consistent comfort across the zone. However, this method requires the fan to run continuously during occupied hours to maintain airflow and proper ventilation. In most commercial WSHP systems, this second method is the recommended and more effective approach for introducing outdoor air. Let's talk about one of the most common challenges in WSHP design: humidity control. On humid, mild temperature days, water source heat pumps often cycle off quickly. That's because the thermostat only senses temperature, or the sensible load, not the humidity, which is the latent load. The result? High indoor relative humidity, creating that clammy, uncomfortable feeling, even when the temperature looks fine on the thermostat. Here's an example. In the morning, when the outdoor air is 68 degrees Fahrenheit dry bulb and 66 degrees wet bulb, the indoor humidity might be around 53% RH. By mid-morning, as conditions rise to 72 degrees dry bulb and 72 degrees wet bulb, humidity increases to about 63% RH. And by noon, with 74 degrees dry bulb and 72 degrees wet bulb, the relative humidity can reach 73%. Even though the sensible temperature hasn't changed much, the latent load, the moisture in the air, keeps building. Meanwhile, the fans continue to bring in more humid outdoor air, and the WSHP doesn't run long enough to remove that moisture. That's why incorporating a proper dehumidification strategy is critical in WSHP system design, especially in warm, humid climates like the Southeast United States. Now that we've covered why dehumidification is so important, let's look at the three main options for conditioning outdoor air in a WSHP system. Option 1. Dedicated Outdoor Air System, or DOAS. A DOAS uses a refrigeration cycle combined with reheat to deliver what we call neutral air, typically around 70 to 75 degrees Fahrenheit dry bulb and 50 to 55% relative humidity. This system removes a large amount of moisture before the air ever reaches the occupied zones. Because the outdoor air is already conditioned, the WSHP units in each zone only need to handle the sensible load, meaning they can often be smaller and more efficient. DOAS units are especially common in schools, offices, and hotels, where humidity control and comfort are top priorities. Option 2. Energy Recovery Unit, or ERU. An ERU transfers both heat and moisture between the exhaust air and the incoming outdoor air using a desiccant wheel or similar media. It's an excellent way to reduce operating costs and is often used alongside a DOAS for added efficiency. However, by itself, an ERU usually cannot manage the full latent load on hot, humid days. It also requires routine maintenance. The wheel, filters, and motors must stay clean and balanced to maintain performance. Option 3. WSHP with built-in dehumidification and reheat. Some WSHPs now come with an internal reheat coil to remove moisture and warm the air before it enters the space. There are three types of reheat options. Hot gas reheat uses compressor discharge gas for reheat. It works, but it's complex and can be difficult to control consistently. Electric reheat, simpler, but comes with higher electrical demand and operating costs. Hot water reheat, the most efficient and reliable choice. It uses condenser water circulating through a hydronic coil to reheat the dehumidified air. With hot water reheat, a modulating valve and proportional controller fine-tune water flow through the coil, keeping the supply air temperature and room conditions steady and comfortable at all times. In summary, whether you use a DOAS, an ERU, or integrated WSHP reheat, the goal is the same. Deliver dry, conditioned outdoor air to maintain indoor comfort and system efficiency. Now let's look at the water side of a WSHP system. Unlike a traditional chilled water system, the WSHP water loop is simple and contains only three major components: a cooling tower, a boiler, and pumps. First, the cooling tower. Its job is to reject excess heat during the cooling season. The preferred choice is a closed-circuit cooling tower, or CCCT. A CCCT has an internal heat exchanger built in, so there's no need for a separate plate and frame heat exchanger. It protects the system water from contamination, reduces maintenance, and minimizes pumping energy. Another advantage is flexibility. Closed-circuit towers can even be installed indoors, which helps maintain a cleaner loop and keeps the equipment out of sight. If an open tower is used instead, you must install an intermediate heat exchanger to isolate the tower water from the system loop. Operation. In that case, a high turbulent shell and tube exchanger is recommended because it's less prone to fouling and easier to service than a plate and frame type. Next, the boiler. During the heating season, the boiler adds heat to the water loop, acting as the primary heat source, similar to what the Earth does in a geothermal system. A condensing gas boiler is ideal because of its high thermal efficiency and ability to modulate with load. However, electric boilers are also a good alternative where gas isn't available, or when a low-carbon design is required by code or sustainability goals. Finally, the pumps. Pumps circulate water between the WSHP units, the cooling tower, and the boiler. For reliability and ease of maintenance, base-mounted end suction pumps with center dropout spacer couplers are recommended. This design allows maintenance crews to remove the rotating assembly without disturbing the piping or motor alignment. Each pump should also be equipped with a variable frequency drive, or VFD, to automatically adjust pump speed based on system demand. This not only saves energy, but also helps maintain stable loop temperature and flow balance under varying loads. Together, these three components form the heart of the WSHP water loop, ensuring efficient heat transfer, long equipment life, and smooth year-round. Each pump should also be equipped with a variable frequency drive, or VFD, to automatically adjust pump speed based on system demand. This not only saves energy, but also helps maintain stable loop temperature and flow balance under varying loads. Together, these three components form the heart of the WSHP water loop, ensuring efficient heat transfer, long equipment life, and smooth year-round operation. Freeze protection for cooling towers. Freeze protection is critical in any climate that experiences sub-freezing temperatures. For open tower system, ensure that basin heaters are installed and controlled by a thermostat at 40 degrees Fahrenheit. A low water cutoff prevents heater burnout. Heat trace and insulation are applied to exposed piping. Fans have vibration cutoffs to prevent damage from ice buildup. For closed-circuit towers, additional protection includes positive closure dampers to prevent heat loss, circulating the loop pump during cold periods, using glycol mixtures to lower the freezing point, continuous monitoring through the BMS to ensure the coil doesn't freeze. Here are the standard control set points for a WSHP loop. The system operates within a deadband range of 50 degrees Fahrenheit to 90 degrees Fahrenheit. When the loop stays within this range, Neither the cooling tower nor the boiler needs to run. The system simply balances energy between zones. When the loop temperature reaches 90 degrees Fahrenheit, the cooling tower spray pump and dampers open to begin rejecting heat. If the temperature continues to climb to 95 degrees Fahrenheit, the tower fan starts to enhance heat rejection and bring the loop temperature down. Once the temperature drops to around 80 degrees Fahrenheit, the tower pump, fan, and dampers all shut down. On the low side, when the loop temperature falls to 50 degrees Fahrenheit, the boiler starts and runs until the temperature rises to about 65 degrees Fahrenheit. The boiler set point is typically maintained around 60 degrees Fahrenheit. This control sequence keeps the water loop temperature stable year-round, allowing each WSHP unit to operate efficiently while minimizing energy use and unnecessary equipment cycling. Key design takeaways. Start with accurate load and ventilation calculations. Maintain hydronic loop temperature between 60 to 90 degrees Fahrenheit. Precondition outside air with DOAS or WSHP reheat. Use closed-loop cooling towers and condensing boilers for high efficiency. Integrate smart controls for loop temperature and equipment staging. Ensure good water quality and flow balance for reliability. Leverage geothermal or hybrid loops where site conditions allow. WSHP systems optimization strategies. Use two-stage or variable speed compressors. Better part load control, less short cycling. Apply diversity factors when sizing the boiler, tower, and pumps. Select variable speed fans with large coil surfaces for greater heat transfer. Use condensing boilers. They thrive on low return water temperatures. Avoid oversizing WSHPs. It causes humidity and comfort problems. Use dual variable speed pumps. More efficient and provide redundancy. Integrate modulating hot water reheat for dehumidification control. Add a heat pump water heater. Capture waste heat to produce domestic hot water. Install automatic flow regulating valves. Stabilize delta T and prevent overflow through units. Water source heat pump systems are the future of efficient, sustainable building design. They combine the decentralization of zone-level control with the energy efficiency of shared hydronic infrastructure. Whether applied in a school, high-rise, or retrofit project, WSHPs deliver comfort, control, and savings, all while supporting decarbonization and net zero energy goals.